Okay, so now we're just going to do what we did before. So these ideas of, but with bases. So, these ideas of a weak base and KB and all of that stuff are going to come into play here. We're going to do an ice table, all of that. And again, I can summarize what we're going to do in one sentence. Time for a new marker, it looks like. So we're going to use an ice table. This is going to sound familiar to start. There's a little twist at the end. So we're going to use this to find. So again, weak bases are making OH minus, not H3O plus. So we're going to find OH minus. Our OH minus equilibrium concentration. And then we're going to calculate our POH, right? Because we have OH minus, not H. But we want to find the pH, right? Because that's our standard scale. Like, that's just what people use. And so we're going to convert it to pH. So remember, POH plus pH equals 14. So if I know this, I just subtract it from 14, and I get this. I get pH. All right, so let's get cracking on the example, right? Again, I'm not going to be very creative. You've seen this weak base equilibrium before. We're just going to bring numbers into it now. So, and then there's a really fun coincidence that cracks me up every time. I'll talk about that in a second. So what is the pH of a 0.250 molar ammonia solution, right? I've shown you ammonia a couple times. Okay, well, Kb for ammonia is 1.8 times 10 to the minus 5. That is a coincidence, okay? It's not that every single acid and base has a Ka and a Kb of 1.8 times 10 to the minus 5. It just so happens that the two I like to work with do, which is great because I only have to remember one number. So if you look in the table in the back of your book, you'll see there are other numbers available. I will use other systems on the practice sheet, so don't keep using 1.8 times 10 to the minus 5 unless you're seeing ammonia, all right? And so our equilibrium expression for this is ammonia plus water. So ammonia is NH3, and that's going to get you ammonium. You might remember that polyatomic ion from 151, and hydroxide. Okay. All right, so we've got our equilibrium expression, so we can write our initial condition. And again, we're going to assume, so this is 2.50 molar ammonia. So we put, enough ammonia in to make this concentration initially. We don't worry about that. We have no ammonium. We didn't put any ammonium in, right? There's nothing in here about ammonium. And again, we're going to say that's 0. So you could be like, oh, it's 10 to the minus 7. You could, and you could do a lot more work and get the exact same number, but we'll just be like 10 to the minus 7 is about 0, right? So for all the same things I talked about in the last video, we're going to say 0 there because it's not a dilute weak base solution. All right, so our change is minus x plus x. We're shifting right, plus x. So things are moving this way. So we're dropping here, we're going up here. So minus x plus x plus x. And so at equilibrium, 0.250 minus x, x, and x. At some point in the next few weeks, I'll just be like, you do an ice table and you get this, but we're not there yet. You haven't seen too many of them, so we'll keep working through. If you've got the hang of the ice table, feel free to just do this problem. See if you can do it, and then see what I do in the video. Make sure you get the same thing. All right, we write our expression for Kb. Stuff on the right over stuff on the left, so NH4 plus times OH minus concentrations divided by ammonia concentration, NH3. And so that's x squared over 0.250 minus x, which equals 1.8 times 10 to the minus 5. And you've seen this exact numerical setup before, so you know what I'm going to do here. X is small, right? We've got a small value here. It's only going to shift to the right a teensy-weensy little bit, And I'm going to say that teensy-weensy little bit is small compared to 0.250. We'll verify. We'll make sure it's less than 1% when we get x, but I have a strong sneaking suspicion that it will be. And so x squared over 0.250 equals 1.8 times 10 to the minus 5, and so multiply by 0.25, square root it, blah, blah, blah. Do the math, right? And you get x. Don't even need to do quadratic formula, right? We just do a little bit of algebra, not even algebra, arithmetic. And we get x equals 0.00212, which, if you looked at the last video, you saw this setup. So, surprise, you got the same number again. So x is the same. Doesn't mean pH is the same, though, but x is the same. All right. And that is less than 1% of 0.250. So it is less than 0.0025. Barely, but it is. So it's less than 1%. Calling it good. I don't need to worry about doing anything more complicated. All right. So at equilibrium, my concentration of OH minus is equal to x, which means that it is 0.00212. So my POH is going to be the negative log. Whoa, I'm way off. Sorry about that. Forgot to drop the paper down. Hope you enjoyed watching my arms right. You can see how much I lean over my desk now. Okay, so we use our result from our ice table to get our concentration of OH minus, and then we just plug that in here. So and we get 2.7. Okay. Looking familiar, but this is where the trick comes in. Okay, we want pH. We've got POH. And just to be clear, those are not the same, right? So what can we say? Well, we can go, well, 14 equals pH plus POH, which means that pH equals 14 minus POH if I subtract POH from both sides. Okay. And so 14 minus 2.7, I get 11.3. So the pH of this solution is 11.3. And again, I'm going to ask, does that make sense? Does it seem reasonable? And I think so, yeah. It's over 7. That's, yeah. That means we didn't make anything too terrible for a math error. So we have a weak base, right? We have a weak base. It's going to drop H plus concentration, or H3O plus concentration, which means it's going to raise pH above 7, and that's what we have here. So always good to take a moment, pause, and be like, does this number make sense? Okay, well, guess what I'm going to ask to close things out here? What's the percent ionization? Bonus question. And then just to back up too. So this is what you do, right? Like if you have a system and you can't directly get to concentration of H+, you can get to concentration of OH- instead. Bases will give you concentration of OH-, get the POH, and then you do this little trick right here. pH equals 14 minus POH. Oops. Okay. Anyway. So I wasn't kidding. I said that like this was a very important relationship. This is where it becomes important. All right, but for percent ionization, we don't need any of that. All right. So what was our formula? Well, our percent ionization was concentration of OH- at equilibrium over the concentration of our base, which in this case was NH3 that we started with, our initial amount. So generally you see a 0 there, it means like times 0, means like initial. And we multiply by 100%. I know Coach always said give 110%, but in science we do 100% max. All right, and you'll find out that it's much less. And so if we plug in the numbers, all right, we got our value for our equilibrium concentration here, the result of our ice table. And how do I know what the initial amount was? It was given to me in the problem. Okay, so I plug those in, times 100%, and it turns out that because KB was the same as Ka for the last example I did, the percent ionization is identical. So it turns out that ammonia only gives 0.848%, all right? Not Coach's favorite, all right? That's slacker ammonia. But yeah, and so that's what we do. So again, ice tables aren't going away. They're not going to go away for several weeks. As long as we're doing equilibrium stuff, ice tables are very much in play. So be aware. Good news is you'll have plenty of opportunity to practice them. So, if there was something not quite clicking last week, it will this week, hopefully. And then the other thing is, you'll notice both examples I did. The weak base, I was able to do X is small. And on the weak acid, I was able to do X is small. So you will find that these Ka values and these Kb values, well, they're not always 1.8 times 10 to the negative 5. They are often quite small. And so because of that, you can do the X is small approximation where you knock it out of the bottom there. All right, so that'll do it for the material this week. I'll give you lots of opportunity to practice. If you have any questions, let me know. Please, don't feel embarrassed if you are struggling with ice tables or anything like that. I want to help you get that straightened out because that's becoming less of a new idea and more of a necessary skill to tackle the new ideas for this week and the coming weeks. And so we will continue through chapter 14 for 2 more weeks after this. So we'll do most of the rest of the chapter next week, and then we'll save the last section for a week all by itself because it is tricky, and we have the time to do that. And so that's where I want to spend the time because that is actually one of the trickier titration curves. Calculating them is a very complicated idea. And so I think it's great that we're able to spend a week on it. And I think hopefully you will feel that way too. Or at least, if not, that it's a great thing that you appreciate that you didn't have to do that on top of a bunch of other stuff that week. But yeah, as always, office hours, message me, whatever. Let me know if there's anything I can do to help.